Hey everyone! Today we're going to dig into the single most critical and honestly, the most often missed step in any kind of data-driven science. We're going to talk about how to stop making the biggest mistake in scientific machine learning, and here's the kicker, it's a mistake that happens long before you ever write a single line of code.
This right here, this is the scene of the crime. You get your hands on a data set, you fire up a notebook, and what's the first thing you want to do? You want to start fitting models, right? Well, that instinct, that jump straight from data to a model, that is the root cause of so many failed projects and misleading scientific papers.
So why is this little jump so dangerous? I mean, it seems harmless enough. Well, it's because when you do this, your entire evaluation becomes completely meaningless. You end up with these amazing-looking metrics that support claims that are just fundamentally false. You get results that can never, ever transfer outside of that one specific data set.
And this really gets to the heart of it. Most of the bad machine learning you see in science, it's not a modeling problem. The models themselves might be fine. It's a process problem. The whole approach is flawed from the get-go because the way the problem is framed is just logically inconsistent with the data you have.
Let's look at what actually happens. When you rush to a model, you can accidentally do things like leak information from the future into your training data. You know, like using tomorrow's rainfall data to predict today's water quality. Or in chemistry, you might get this incredible performance, but it's only because your training and testing data have almost identical chemical structures. It's an illusion of generalization. It's not real.
So, how do we fix this? What's the antidote? Well, we need a framework. We need something that forces us to slow down and think like a scientist before we think like a data scientist. We need some structure. And that solution is the research problem ladder.
Every single solid scientific modeling project has to climb this ladder, step by step. You start with a real-world phenomenon. You ask a question about it. Then, and this is important, you form a specific, testable hypothesis. Now, here are the crucial middle rungs that everybody skips. Operationalization, which is just a fancy way of saying, how exactly are we measuring this? And then, finally, choosing a metric that really reflects what truth means for your problem. You know, most bad science comes from jumping straight from the question down to the metric.
Let's make this real with an example. So the phenomenon is that water gets contaminated after it rains. Simple enough. Our question is, does that rainfall actually increase E. coli risk? The hypothesis gets really specific. Okay, we think the probability goes up within 72 hours of rain. Now we operationalize. Our target, what we're looking for, is any E. coli level above 0. And our metric, we're going to use recall because for this problem, we care most about not missing a contamination event. See how structured that is? No ambiguity. Okay, once you've climbed that ladder and you have a solid hypothesis, you have to make a commitment, a scientific commitment. You have to choose one of 4, and only 4, fundamental questions that your data is actually allowed to answer. And this isn't a modeling choice. This is a decision about the kind of claim you are making to the world. First up, we've got descriptive. This question just asks what patterns exist. And let's be really clear here. This is not a failure. It's not a lesser form of science. It is a form of scientific honesty. When your data set is small or it's purely observational, just describing the patterns you see is the most truthful claim you can possibly make. Next, we have predictive. This is all about forecasting, right? It asks, what will happen? This is what you use when you're trying to predict something for a future time, or maybe a new location you haven't monitored before, or a brand new chemical compound. The absolute key here is that good prediction requires a genuinely difficult and totally separate test set that represents a true unknown. Third is the explanatory frame. This one asks, what variables are associated? This is all about understanding relationships and seeing which features seem important. But, and this is a huge but, here's the critical warning. Association is not causation. I'm going to say that again. Association is not causation. It doesn't matter how strong a correlation you find, you cannot claim one thing caused another from this frame. And that, of course, brings us to the most powerful and, let's be honest, the most abused frame of all, causal. This asks the ultimate question, what would change if we intervened? This is the gold standard for understanding cause and effect, but it demands an incredibly high standard of evidence, like a randomized controlled trial. Most open datasets will tempt you with causal questions, but very, very few can actually answer them. Just look at the language on this slide. A single word change makes all the difference in scientific integrity.
You can't use observational data to ask if a fertilizer causes a nitrate increase. You just can't. But you can absolutely ask if fertilizer use is associated with it. One is a valid, honest, explanatory question. The other is a false causal claim.
So we've got our hypothesis, we've picked our frame. Now it's time for the moment of truth. We have to design a fair test for our claim. This is where your evaluation design comes in. And guess what? This is also a scientific act.
Okay, if you only remember one thing from this whole explainer, make it this. Your train test split is not just some technical chore you have to do. It is a scientific claim. It is your theory of generalization. It is your definition of what the future or the unknown even means for your specific problem.
And that claim you're making is encoded in how you choose to split your data. For water quality forecasting, you absolutely need a temporal split to stop future data from leaking into the past. For drug discovery, you might use what's called a scaffold split to make sure your model can generalize to totally new types of molecules, not just slight variations of ones it's already seen.
And listen, this one is huge. Random splits are the default in almost every machine learning library, but they are almost never valid in real science. Why? Because most scientific data isn't independent and identically distributed. Observations are connected by time, by physical location, by the batch they were run in. A random split just shatters all those connections and makes your problem artificially easy.
Finally, choosing your metric. This isn't just a math problem. It's a value judgment. It encodes the cost of being wrong. So if you're predicting water contamination and you prioritize high recall, that means you'll have more false alarms, but way fewer people will drink unsafe water. If you prioritize precision, it's the opposite. When you choose a metric, you are choosing who gets harmed when your model fails.
So this all comes together in one final, really powerful idea. Before you even think about pre-processing data or training a model, you have to create and commit to a scientific contract. Think of it as a binding agreement you make with your data and with your research question. This contract has 3 items that, once decided, must be frozen in place. They are non-negotiable. First, your exact target variable. Second, your chosen frame. Is it descriptive, predictive, explanatory, or causal? And third, your splitting strategy. Once these 3 are set, they cannot be changed. All the work you do from here on out has to respect this contract. And that leaves us with this. The next time you read about some amazing new AI breakthrough in science, you now have a tool to look past the hype. Don't just ask about the model's accuracy. Ask a much, much better question. What was their scientific contract? Was the claim they made actually consistent with the data they had?